Guess what? We're getting ready to do another family of functional groups. Oh yeah, that is right. We have went through the alkane family. We have went through the alkene family. And now we're getting ready to go through the alkyne family. Well, as you can imagine, it probably has something to do with some bonds that are shared between some carbons. Alkane, alkene, alkyne. You can almost make $1 million song with that. All right, so in this lecture module, we are actually going to focus on both as far as nomenclature and reactions. Now, you're probably saying, well, wait a minute, we've had a whole lecture on just nomenclature for alkenes, and then we had a whole module on just reactions for alkenes. So how on earth do you expect me to learn the nomenclature and reactions of alkynes all at once? And the answer is it's going to be very easy. And the reason it's going to be easy is because it's a review. Because everything that we've learned about nomenclature for alkanes and alkenes actually applies to alkynes. The only difference is we have to figure out how to incorporate the triple bond. And you're going to easily adapt your method in order to name these the correct way. Okay, well, what about the reactions? There were tons of reactions back in the day that we had to learn on alkenes. Well, guess what? There's tons of reactions for alkynes. But here's the good news. The good news is that all of the alkene reactions apply to the alkyne reactions. The only difference is that sometimes it's a two-stepper, folks. That's right. So we add HBr in the first round and we see what happens, and then we add HBr again in a second round and we see what happens. If you know what goes on with an HBr addition, the same thing holds true with alkynes. And go back and remember what I've been telling you. Foundation first. And then we build the house on it. And this is our organic house that we're building together. So all of those old things back in Module 1 and Module 2, they're all going to come back. And I hope that you're ready for it. All right, so let's focus on the world of alkynes. Okay, so alkynes are carbon triple bond carbons. Go figure. Okay, so we've talked about alkenes, and we said that alkenes were carbon double bond carbons, and we've talked about alkanes, and alkanes are carbon single bonded carbons. All right, well, the world of alkynes focuses on a triple bond. These were sp3 carbons, these were sp2 carbons, and finally we're at sp carbons. Let's talk a little bit about geometry. Do you remember geometry about the sp? I hope you do, because we can bring it back. The sp carbon is a linear type of carbon. As you can imagine, this triple bond with one other bond on the other side of carbon, on either side of carbon here, this makes this bond angle very flat. So we say it's very linear. If you go back and take a look when we were discussing geometries of these carbons, that's one of the things that we were saying. So if we want to talk about angles, we can. This is a 180-degree angle. It's a very flat area of a molecule. But more importantly, folks, look at this. This is a triple bond. Each one of these lines represents 2 electrons. There's a total of 6 electrons that are here. 6 of them. So you talk about a very electron-dense area of the molecule. Alkynes, they got it popping, folks. I mean, 6 electrons to give away. This is a very negative area of these molecules. And negative areas very often lead to very good nucleophiles, another definition that we've talked about before in the past. So, with the alkyne family, I have a very flat area. I have an area that is somewhat saturated with negatives that we call electrons. It makes very good nucleophiles, and because of that, These alkynes, they are very exposed. And that means if they're exposed and if they're wide open and basically saying, hey, right here I am, here's all my electrons, come and take them, then what happens is that the alkyne family is very reactive. Now, I know what you're probably thinking. Well, wait a minute. There's extra glue between these carbons. They're pulled in a little bit closer together. We talked about bond lengths of alkynes back in the day. Yeah, that is true. They are getting closer together. Those electrons are pulling it together. But that has nothing to do with reactivity. Reactivity has everything to do with nucleophile and electrophile, and as we can clearly see, this is a very good, strong nucleophile that we can use. All right, so let's talk about the general templates. For an alkane, we said that these were typically carbon with a certain number and hydrogen that has doubled it and added 2 more, right? Okay, so this is perfectly fine. This is just a review. Well, in the world of alkenes, we said that we can have a carbon, certain number, a hydrogen, and we'll double that number. The reason that we don't add 2 is because 2 of those hydrogens had to be taken away to create the extra bond between those carbons. So what do you think alkynes are going to be? Oh, yes, sir. Yes, ma'am. You got it. We're going to take away another 2. So this is a 2n minus 2. So the first subtraction of 2 creates the extra bond that we call a double. And then another 2 that gets taken away will create another extra bond that we're going to call a triple. All right, now keep in mind cyclics. Cyclics are out there. Okay, so if an alkane has formed a cyclic molecule, then this is a carbon, certain number, and H2N. So cyclic alkanes actually have the same template as alkenes do. And that's the problem with the template. That's why we don't use it often, because there's a lot of things that can begin to happen that really throw this equation out the window, and it doesn't make sense anymore. And here is one of those. These two things have the same formula, but they are 2 different structures. All right, well, if alkenes form a ring and we have a cyclic alkene, well, we did have 2n, right? But we have to subtract another 2 in order for that ring to form, because those carbons have to connect together. So we see that alkynes actually have the same template that a cyclic alkene would. And again, it complicates our answers up. And then, can we have a cyclic alkyne? And the answer is, yeah, we could, even though they don't really stay around that long, but we could. And the cyclic alkynes, if that's the deal, this is where the alkyne would start. So we have to erase 2 more in order to get that ring. And a cyclic alkyne would have the template of CN H2N minus 4 at this point. Now, something else that we want to say about alkynes. Very few of them are what we would call natural. Alkynes are somewhat unstable. They have a flat area. They're very exposed. They're really good nucleophiles. They are heavily electron dense. So whenever they can get rid of all of that, whenever something wants to come in and take advantage of them, well, those things are going to take advantage of them. Don't be an alkyne in life. Don't let people take advantage of you, okay? So very few natural alkynes are left over. But there is one that is major in the world of not just laboratory sciences, but other fields as well. And this alkyne is pretty important. And we call this alkyne ethyne. E-T-H-Y-N-E. This is the IUPAC name for that compound. Could you guess what structure this is? I hope you can say yes. What does F mean? F means 2. 1, 2. And what do you think the YNE represents? That's right. That is our ending that we begin to use in IUPAC nomenclature. Can you believe it? Alkynes end in a YNE, and IUPAC names will end in a YNE. Okay, so that means that this is a carbon that's triple bonded. Okay, well, there's only 3 bonds on each one of those. That's not a problem. Our 4th one, of course, will come from hydrogens if they're not drawn, and I can draw these just to kind of clean it up. And this is the structure of ethine, a very important alkyne in the world. Why? Well, if I give you the common name might be a little bit better for you. The common name for this structure is acetylene. Acetylene is a gas. Acetylene is used in welders' torches. It's used in the laboratory to measure metals, maybe in a water sample or a soil sample, things like mercury and lead and copper and zinc, iron. Well, maybe not mercury. Mercury is typically a cold vapor method. But acetylene is the world of atomic absorption for us. But it also puts together pieces of metal at a very high temperature, and you have to put a face shield on so you don't get a face full of sparks. That's also acetylene. Okay, so if this is the common name, I have an issue with it. And here's the issue. ENE. That's where people have problems. They look at acetylene and they see ENE at the end and they think alkene. And they think that this has a double bond. It does not. Don't ask me why. I don't make the rules. I just tell you the rules. That's all that I do. So at some point in time, someone thought that a very good name for this would be acetylene, and they ended it with an ENE. And now, all of a sudden, people get confused because they think double bond is present when it's actually a triple bond. So do not let this common name throw you for a loop. It's one of those that I told you that organic doesn't quite fit in a box every single time that we try to put it in one. And here's one of those examples. So acetylene is a carbon triple bond carbon. It is an alkyne. However, it doesn't end in YNE, and that's the problem that people begin to have with that particular common name. All right. Good news is that we don't have a lot of common names that come along with alkynes, but when we do, it's this one that we try to integrate into the common name just so that we can keep it active and fresh. Now, let me show you a picture. Here's an image of 1-hexyne and 3-hexyne. 1-hexyne is what we call a terminal alkyne. So what happens if you have a terminal disease? That means that you're at the end most of the time, right? So a terminal alkyne means that it's a triple bond that is at the end of a molecule. And here we see it. We see a carbon, and these are triply bonded. There's the alkyne structure. How do I know that? There's one hydrogen over here. That's it. Just one hydrogen. And this carbon doesn't have anything on it. It's connected to another carbon. So right there are the 4 bonds that are associated to each one of those. If you look at the 1-hexyne, and you look at this terminal alkyne, you see that this area, folks, is very flat. It sticks out like a sore thumb. You can actually see it pointing up, saying, hey, right here I am. I'm a triple bond. I've got all of these electrons. Come and get them. I'm ready. Oh, gosh, could you imagine? All right, now down here at the bottom is 3-hexyne. This is a carbon, and they're triply bonded in between. We have a bond to the right and a bond to the left. This goes to another carbon. The one to the right goes to another carbon, but we call this an internal alkyne. Why? Because it's on the inside of the molecule. It's not on the outside. So out of these two, the terminal alkynes are going to be more exposed. We do get a flat area in here. Don't get me wrong. We do have a flat area. We can see that. However, the one on the ends are more exposed than the one in the middle. So out of these two, which one's more stable? We're going to say the internal alkyne is more stable. And then the terminal alkynes would come next. Why is that? Things can see these a little bit better. Another globby molecule can come in here and sit right on top of that triple bond and start plucking away. Okay? Well, if this molecule decides to come around and decides to attack this molecule, it has a very limited space in order to get in here. You know, these carbons, they do take up room. These hydrogens, they do take up room. This is a simple alkyne anyway. I mean, could you imagine if we had big, longer R groups that are on this thing? So it's a little bit harder for those molecules to get in there. Now, let's talk about nomenclature rules. So here's my nomenclature lesson for you. Follow rules as before. That's it. That's all you got to do. We just have to modify our ending, and the C triple bond C area gets a YNE at the end of the name. That's it. It's one of the few modifications that we have to make. And then in addition to this, when we pick out the longest carbon chain, we want to make sure that we are including the triple bond if we can. So if that triple bond is present and if there's no other groups that really kind of take it over, then we want to make sure that those longest carbon chains have the alkyne in place. So let's do a few examples of these. And the example that I'm going to start with, what if we needed to draw 1 bromo, 5 methyl, 3 hexyne. Can you do it? Pause me. Attempt it. I know that this is our first example with alkynes, but it doesn't matter. I think that you can do this if you really just kind of think about each individual piece. So pause this video, try to draw that molecule, and then do it, and then push play and see if you get a correct answer. All right, so maybe you're here to check an answer. Maybe you're just here to get the answer. Who knows? I really don't know. And I'll just keep on moving. That's okay. Let's take a look at this example. 3 hexyne. Hex means how many? 6. 1, 2, 3, 4, 5, 6. We're on a good roll. 3, what do you think the 3 represents? It's the carbon that has the YNE. That's the carbon that has the triple bond. 1, 2, 3, and here we have a triple bond. I can draw it that way. That's perfectly fine. Look at me and I'm on a roll. 5 methyl. Just working from inside out. All right, 1, 2, 3, 4, 5. Here's the 5th carbon. I'll draw down. Looks like that's where it would want to go anyway. And I'll put a methyl group of 1 carbon piece. And then 1 bromo. On the 1st carbon, it's right here. Well, I could go down if I wanted to, and I could draw the BR like that. That's okay. But if you wanted to kind of draw it out to the side and put the BR there, that's all right too. Whatever makes you feel good. Either one of those is perfectly fine. Well, some people, and there you go, folks, that's all there is. So some people like to focus in on this triple bond, and what they do, and I never really do that, but computer models will do it for you. They will focus on this triple bond, and they will make sure that this triple bond is a flat area of the molecule. So what they will end up doing is that they'll take a look at this carbon to the left, and they'll say, hey, we've got a 1-2 piece with a bromine. So 1-2 piece, and we have a bromine that comes off of it. And then over here to the right hand side, this carbon looks like it has an isopropyl group, right? So 1, 2, and 3. So there's our 3 carbon. So they will put a focus on this triple bond. They will make sure that it's flat. They will make sure that it's the center of the molecule. I just don't do this, and I'm perfectly okay with it naturally happening from your hand on a sheet of paper. So seeing this is really no different than seeing the version to the right-hand side. I am not particular when it comes to this stuff. So, folks, what you see on the left-hand side that we did together is perfectly okay. But keep in mind that in a textbook or in Blackboard or in a piece of literature, they will try to give you a flattened version that will look like something over to the right-hand side. They just want to focus that triple bond in the center. They want to make sure that it is flat all the way across and that it's not drawn at an upward or downward angle. Don't ask me why. That's just what they want to do, I guess, to make sure that they get the point across that it is a flat area of the molecule. All right, so let's take a look at some other structures. So let's take CH triple bond CH. We did this one already. This is a 2-carbon chain, and this is going to be called F. Normally it would be ethane, right? And then we would change this to ethene if it was a double bond, but now we're going to change it to a YNE, which represents the triple bond. So ethyne is the name of that structure. All right, we'll do another one. CH3, CH2, carbon, triple bond, CH. So I look at my longest carbon chain. This is a total of 4. So butane. All right. Well, I know it's not an A because that would be alkane, single bond. I know it's not an ene. That is a double bond. So therefore, this is an ine. Look at this, folks. We are doing review of nomenclature on alkanes and alkenes as we do alkynes. I told you it is a constant review, which is why the final is very easily cumulative, because all of these things go hand in hand. I am just wrapping it all up into a nice little Christmas package once again for you. So butane, and I need to kind of tell you where that triple bond is at. 1, 2, 3, 4. So at the first carbon, because I'm going to number closest to that end, I'm going to have the YNE. I can put the 1 here. If I don't put the 1 here, though, it's understood to be at that first carbon. All right, so there we go. Let's do another one. We'll do CH3, carbon, triple bond, carbon, CH2, CH3. Okay, longest carbon chain, 1, 2, 3, 4, 5. So this is a pentyne. There you go. You're on a roll. Good for you. Where's that triple bond? What number carbon? If I number from the right, that's the third one in. If I number from the left, that's the second one in. I number from the left. And this is a 2-pentyne. That's it. No more groups that I need to name. We'll do another one. CH3, CH. I'm going to go up. CH2, CH3. Then we'll do another carbon, a triple bond, a carbon, and a CH3. Name it. Okay, not a problem. I do the longest carbon chain. Let me go across. 1, 2, 3, 4, 5. Wrong. No. That's not your longest carbon chain. They're trying to trick you. If you go all the way across, that's 5. However, what if you start it from the right-hand side? And you do 1, 2, 3, 4, go up, 5, and 6. Oh, there's my longest carbon chain. They tried to get me, but it didn't work, did it? All right, so this is a 6-carbon chain. That means this is a hexyne with a YNE. A number closest to the end with a triple bond. All right, so I start left, up here at the top. 1, 2, 3, and this will give me 4. And then I go and try right-handed and go that way. 1, 2, stop. There you go. There's your lowest number. That is the way that you need to number this chain. You give that triple bond the lowest number possible. So this is carbon 1, this is carbon 2, that's carbon 3, this is carbon 4, there's 5, and there's 6. So on carbon number 2, I have the ine group. That is where my triple bond is located. Notice that I didn't look at anything else. I didn't look at anything else, did I? I gave the priority to that triple bond. Well, we're not quite done, because on carbon number 4, I have a group, and that group is called a methyl group. So 4-methyl-2-hexyne is going to be the name of that structure. Okay, those are IUPAC names. Now, let's talk about common. I told you we don't use them very often, but with the simplest alkynes we can, and each one of these we can give you a common name, and this is how we do it. Up here at the very first one, this carbon triple bond carbon, we've already talked about the common name for that. The common name here was acetylene. Acetylenene. That is the welder's torch. That is the gas that's required to make that super bright flame. Not only for a welder's torch, but for our equipment in a laboratory as well. Yes, it does that. Well, we're going to keep that trend. And in the common names with all the other ones, wherever that C triple bond C is, that is what we're going to call acetylene. So in our next example, I'm going to circle this area. This is going to be our acetylene group. All right, so it's some type of acetylene. What type of acetylene is it? You name the thing that's on there that you haven't circled. That's how this works. So what do you call this? A 2-carbon chain. I hope you tell me ethyl, and if you do, you have just made the common name. Ethyl, and I don't know why that looks like a B, an ethyl acetylene. That's how you handle these common names, folks. If you look at 2-pentyne, how do we do this one? All right, well, same deal. You circle this, and that C triple bond C stands for acetylene. All right, then you name the groups that you haven't circled. What's over here to the left? A methyl. What's over here to the right? An ethyl. Alphabetize them. Okay, E comes first, so this is ethyl, and then the methyl, and then the word acetylene. Ethyl methyl acetylene. There's your common name for that structure. All right, whoa, what about this one? Okay, well, let's check. Maybe it doesn't have a common name. Maybe it does. But let's see if we can get creative. Here's my C triple bond C. So there is the acetylene group. To the right-hand side, this is no big deal. That's a methyl, right? That's the easy one. What about over here to the left? Do we have a common name for something that looks like that? Yes, we do. Count the number of carbons. 1, 2, 3, 4. This is a bute. Is it an isobutyl? No, it's not an isobutyl. It doesn't quite make the L at the very end with those 3 carbons. But this carbon is on a secondary carbon of the butyl. So this is a sec group. And keep in mind that the S for sec and tert for T, those do not get alphabetized. So this is a B for butyl and an M for methyl. So this is a sec butyl methyl acetylene. Folks, that's how we do our common names for alkynes. We use acetylene as the base, and then we name the groups on either end. Sometimes, and very often, those molecules are going to be much more complicated than this on the screen, so we will not be able to give you a full-blown common name very easily, and we begin to stray away from them. IUPAC is where it's at. It always has been, and it always will be from this point on. So, that's where this video is going to stop. And in the next one, we're going to continue on with nomenclature. We're going to look at other molecules, maybe bigger molecules, maybe molecules with more groups on them, more substituents on them. How can we actually handle those and name those on a sheet of paper according to the IUPAC rules? And that is what you'll learn in the upcoming videos. So, guys, what I'm telling you right now is that I know that this might seem a lot of information in the beginning, but this is a rehash. It is a rehash of everything that we've already learned about. The difference is that it's applied to a triple bond and not a double and not a single. Even when it comes to the reactions later on in this module, it's a rehash. It's the same reagents, it's the same mechanism, it's the same everything, except it's on a triple bond instead of a double. So that is why we group both of these topics together into one nice little delivery that we can hand deliver to you at your home if you're watching this online through a series of lecture videos. All right, so stay tuned. Do you need to take a break? No, you got this. You can keep on trucking. You know what to do. Your hand is all stretched out, your knuckles are cracked, and you are ready to learn alkynes. I know it, I can feel it, I can sense it, I can hear it. So good luck in this lecture module, and in the next one, we'll continue with IUPAC.